In this video, we're going to look briefly at electron dot structures and then focus more on molecular shape and polarity from page 8 of your homework packet. So I'm going to pull up a document here and I'm going to grab a marker. So if you look at page 8 of your homework packet, number 5 says for each of the following molecules, draw a Lewis structure, electron dot structure, then determine the shape of the molecule, and then determine whether the molecule is overall polar or nonpolar. And I took example A and C from there, and I'm going to just show those right here. So as far as electron dot structures, I'm going to briefly talk through it. I have some rules up front here. And it says add the number of valence electrons in each atom to determine the total number of valence electrons. So what I did was I took 2 electrons, there's 1 valence electron in hydrogen, but I have 2 of them. So 2 times 1 would be 2 valence electrons. And then oxygen, I have 1 of those with 6 valence electrons. For 2 plus 6 would be a total of 8 valence electrons. Okay, next thing I'm going to do is start with the atom closest to the center of the periodic table, the one that bonds the most, okay, the one with the fewest valence electrons, excluding hydrogen. So I'm going to start with the oxygen. And what I do is I put 1, 2, 3, 4 electrons around, then I start doubling up 5 and 6. So I covered the 6 valence electrons for oxygen right here. And then it's like, oh, there are 2 bond sites, and I have 2 hydrogens, and each hydrogen has 1 electron. These are kind of the darker electrons right here. So I put 1 of those hydrogens right here. I put another hydrogen right here. And ultimately, what happens? Atoms bond when electrons need to be shared to complete an octet. So oxygen had 6 around it before, but now it has 2, 4, 6, 8 around it, so it has an octet. The total number of electrons in the structure is 8, and it is here, 2, 4, 6, 8. And everything's full with 8 electrons, except for hydrogen is full with 2, and I have 2 around the hydrogens, so that's full too. So this would be my electron dot structure for H2O. For CF4, I do it similarly, except I have 4 valence electrons in carbon. I have 1 of those for a total of 4. I have 4 fluorine atoms, each one with 7 valence electrons. 4 times 7 is 28. So I had the 28 valence electrons from fluorine to the 4 from carbon. I get 32 valence electrons. That's what I should have in my structure. If I start to build this structure, I take the central atom, the one that bonds the most, closest to the middle of the table, which is carbon. And it has 1, 2, 3, 4 electrons. Looks like 4 bond sites. Those are the 4 circled 4 hollow electrons, I guess we'll say. And then what's going to happen is the ones that aren't filled in. And then I'm going to take the fluorine, which has 7 valence electrons, and go 1, 2, 3, 4, 5, 6. It's already doubled up there, 7 electrons, and I'll attach that there. Now this fluorine has 7 of its own electrons. It shares with a carbon to get to 8. I do the same thing with this fluorine here. I do the same thing with this fluorine here. I do the same thing with this fluorine here. Ultimately, I have 8, 16, 24, 32 total electrons. I have an octet around this fluorine and this fluorine and this fluorine and this fluorine. And by bonding 4 times, now the carbon has 2, 4, 6, 8, an octet there. So we follow all our rules, and this is a stable structure. All right, let's look at shapes of these things and then whether the molecule is polar. That's kind of the bigger piece that we have. I'm going to take this H2O molecule, which looks like this. Okay, or you can say like this, the red one is oxygen and the white ones are hydrogen. Okay, and why does it look like this instead of linear like this? Okay, it's because there are spots for these unbonded electron pairs. So it's really taking a tetrahedron-like structure like this, and 2 of these things would be removed and putting an electron pair right there. So what happens is I end up with a bent structure like this. If I were determining the shape, what I would do is I would look at the shape guide. I would look at the central atom, which is oxygen, the one bonded the most. and I would say, oh, that's in family 6. And then I'm going to go over to family 6 on my shape guide. It really helps to see the molecules in the room, but I have a visual of the molecules online under the one labeled visual, so you can see that. But let's go to these shapes right here. Just need to scroll down a second. Scroll down, and I'm going to say oxygens in family 6. 1, 2, 3, 4, 5, 6. And what happens, I have an O with 2 things attached. In this case, it's hydrogen. So it's H2O. And I can see that that shape is bent. Okay, and that is the bent shape that I'm talking about. So that is going to be the shape right there. Okay, so I just go back here, and then I can write in the shape. I think I'll do that. And just say for shape that it's bent. Maybe I'll do that over here. It's bent. Okay, now the other thing it says, determine whether the molecule is overall is polar or non-polar. So we have an electronegativity chart. I think I look up here and I can see that I have an electronegativity difference of hydrogen is 2.2, oxygen is 3.0. What's the electronegativity difference? It's 3.0 minus 2.2, which equals 0.8. And 0.8 is individually, those are polar covalent bonds. Okay, let's go look at our electronegativity chart. And this is where I got the 0.2 from for hydrogen. And I got the oxygen as, oh, it's 3.5. Looks like I have a mistake there that we'll have to correct. And the difference actually is 1.3. So I'm going to say, do a little changing here. Let's do a little crossing out here. And I'm going to say that that is what? 3.5 minus 2.2. Let's try that again. 3.5 minus 2.2, which equals 1.3. Okay. Now we said it was polar covalent. Is it still polar covalent? Yes. So the individual bonds are still polar covalent because, let's take a look here, is my electronegativity difference here. To be polar covalent, the individual bonds have to be between 0.4 and 1.7. So polar covalent individual bonds are between 0.4 and 1.7. 0.8 was in between there, but 1.3 is in between there as well. So I'm going to say that that is the electronegativity difference is this right here. Now, the other thing to be polar covalent, the dipoles are not canceling each other out. So we got to look at our structure right here. And we can go back up here if we want to. And do these dipoles cancel out? No, it's more negative by this oxygen, more negative up here. So near the top, it's more negative. Near the bottom, it's more positive. So this tends to be the negative part of the molecule. I'm going to draw an arrow maybe just on this, showing it tends to be more negative to where the arrow is pointing and more positive down here. You don't have to do this, but sometimes I'll put a little squiggle mark with a positive by the hydrogens because it's more positive there, and it tends to be more negative up here, but they aren't canceling out. If it were linear like this, would the dipoles cancel out? Yes. Okay. It would be what? More negative going this way and this way, and it would cancel out. But because it's bent, it's going to be more negative toward here, here, and where these electrons are, it's more negative. So what can I say at the end? I'm going to say overall, this molecule is polar, or you could say it's PC. And why would you say it's polar PC? Because the dipoles do not cancel out. There's a negative region by the oxygens or positive by the hydrogens. Okay, let's do the same thing for the CF4 and figure that out. Now, I think I did this a little bit better here. I said that we had a 4.0 for the electronegativity of fluorine and 2.5 for carbon for a difference of 1.5. So let's just take a look at that, see if that's correct. And I'm going to go over here and see, yes, carbon is 2.5, fluorine is 4.0, the difference is 1.5. 1.5 are polar covalent bonds. But do the dipoles cancel out? Because in order for the whole molecule to be polar, we have to have an electronegativity difference in the bonds, which we have. But we got to make sure the dipoles don't cancel out. All right, so I'm going to go back up here. Oh, and I probably should give the shape of my structure here too. All right, so we got to do that. Let's just throw this in. And I'm going to say the shape of this structure is a carbon is a central atom. It's got 4 fluorines attached. So I'm going to go to family 4 and say, oh, 1, let's go to family 4A right up here. And I got 1, 2, 3, 4, and it's a carbon with 4 hydrogens. This time I put on 4 fluorines. You can't see it right there, but that is tetrahedral. It's this shape right here. So it's a carbon with 4 fluorines, and that would be tetrahedral right here. Okay, just slide that down so you can see that. Family 4A, you got CH4, CF4 in this case, and it's tetrahedral. Okay, we'll write that in. Come back up here. Call this tetrahedral in the box. And then the next thing we're going to do is just look at this. We said we had an electronegativity difference of 1.5 and said that that was polar covalent. But do the dipoles cancel out here? And I'm looking at this, and when you have 4 things attached, what happens is there's a pull in all these directions, but it's symmetrical and it's equivalent. So there's a pull toward fluorine here, 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 and here. Dipoles do cancel out in this family. So overall, this is the dipoles do cancel out, making it a nonpolar molecule. So just coming down here to the shape guide, even though I have an electronegativity difference of 1.5, which makes polar covalent bonds, because in the tetrahedron, with all things being the same, they cross out, the tetrahedron symmetrical, it ends up being a non-polar covalent molecule. Even though I have a big electronegativity difference, it's an either or. The dipoles cancel, making it nonpolar. In order to be polar, we'd have to have the 1.5 electronegativity difference and have the dipoles not cancel. Okay, the dipoles cancel, so it goes over here. So overall, this is a nonpolar covalent molecule right here. Just going to draw this in over here, and I'm going to say these individual bonds are polar covalent, but overall, it's going to be non-polar, or you could say NPC. And why? Because the dipoles, we'll say dipoles, or the polar parts, cancel. Okay, so you get these arrows pulling this way, this way, this way, and this way, but there's not really a pull in any direction because it's symmetrical all the way through. All right, hope that helps with Lewis structures, using the shape chart to determine the shape based off the central atom, and then finally figuring out individual polarity and then whether an over molecule is polar or not. Thank you for watching.